Welcome back to linear algebra. In this video, I want to talk about orthogonal matrices. If you read the title and are having trouble trying to visualize what it means for two matrices to be at right angles to each other, that's not quite what we're talking about here. So that's not the picture we're looking for. An orthogonal matrix is a matrix comprised of orthonormal vectors in its columns. Let me get my head out of the way and I'll be a little bit more specific on what I mean. Let's let Q be any m by n matrix. I claim that the columns of Q form an orthonormal set if and only if Q transpose times Q is equal to the identity matrix I. That seems a little bit outlandish at first, but the proof is actually fairly simple. Let's write Q as a matrix formed by column vectors. Little q1, little q2, all the way down to little qn, right? It's an m by n matrix, so it has n columns. Each of the columns has m rows, so each q1, q2, down through to qn are each vectors in Rm. And when you have a matrix defined by column vectors, then the transpose of that matrix is defined by those same vectors as row vectors, q1, q2, all the way down to qn. And then, see if I can fit this all on the screen, but I don't think I'll be able to. If I multiply q transpose times q, remember matrix multiplication, we want to take the row of the first matrix and dot it with the corresponding column of the second matrix. So it's going to be q1.q1, q1.q2, all the way down through, right? Q transpose times q is going to be the matrix q1.q1. So every entry in this matrix, it can be written as a dot product of two of these column vectors. Now, what I wanted to prove was an if and only if statement. So far, I haven't done anything to address that. I've just given some notation, some naming to the matrices in question. One of the conclusions we had was that Q transpose times Q is equal to the identity matrix. Well, looking at what Q transpose times Q means, this is true if and only if Qi dot with Qj is equal to 1 on the main diagonal where I and j are the same. So 1 if I is equal to j, and the identity matrix is 0 everywhere else. So 0 if I is not equal to j. But this definition, qi dot qj, is 1 if I and j are the same. Every vector dot with itself is 1. The norm, the magnitude of every vector is 1. Take two different vectors, two distinct vectors, and dot them together, you get 0. So this is true if and only if the set q1, q2, down through to qn is orthonormal. So the matrix product q transpose times q is equal to the identity matrix if and only if the column vectors of q are orthonormal vectors. When we talk about an orthogonal matrix, we're looking for a matrix that has this property, although it turns out that for convenience, it's beneficial to be a little bit more restrictive. So we're going to look for a square matrix where the columns form an orthonormal set. And that's what we mean when we say we have an orthogonal matrix. Right? So the matrix isn't orthogonal to anything. The column space of the matrix is given naturally an orthonormal set as its basis. And that in and of itself is going to have some very valuable properties. First property, Q is an orthogonal matrix if and only if Q inverse is equal to Q transpose. This is, again, an if and only if statement, so we have to be careful to prove it in both directions. Or we could use a series of if and only if statements. Right? Q is orthogonal if and only if its columns form an orthonormal set, and we just proved that a matrix has columns that form an orthonormal set if and only if Q transpose times Q is the identity matrix I. Thinking back to things we've proven before, the inverse of a matrix is unique. The only way you can multiply sum matrix A times Q and get the identity matrix is if that matrix A is Q inverse. That means that Q transpose times Q is equal to I if and only if Q transpose is equal to Q inverse. I love proofs like this. It's a powerful statement. The proof is very short, but it is so action-packed. We are leaning heavily on things we've done before. We spent almost an entire video just proving that the inverse of a matrix is unique. So we can use that now without having to say much of anything. We spent, what, 5 minutes proving that Q transpose times Q is the identity matrix if and only if you have an orthogonal matrix. We can rely heavily on that. We're good to go. That's all it takes. All right, here's a quick example. The rotation matrix R. Remember that for any two-dimensional vector, if you multiply that vector by this matrix, cosine theta, sine theta, negative sine theta, cosine theta, that will cause the vector to rotate by an angle theta in the right-hand direction, counterclockwise usually, in your coordinate plane. You'll have the same magnitude, just rotated by whatever angle theta is. I claim here that no matter what angle theta you use, this forms an orthogonal matrix. Proving that a matrix is orthogonal is very straightforward. Find the transpose of that matrix. In this case, that's going to be cosine theta, negative sine theta, cosine theta, and then multiply R transpose times R. All right. First row, cosine sine. First column, cosine sine. We have cosine squared theta plus sine squared theta. First row, second column, cosine times negative sine. So negative sine theta, cosine theta. Then we have sine theta times cosine theta, so plus sine theta, cosine theta. Second row, first column, negative sine theta times cosine theta. Um, then we have cosine theta times sine theta, so plus sine theta, cosine theta. Then we'll take second row, second column. Negative sine theta times negative sine theta is sine squared theta. Cosine theta times cosine theta is cosine squared theta. And you'll notice here that on the off diagonal, minus sine cosine, positive sine cosine, those things are going to be 0. On the main diagonal, you will notice the Pythagorean identity. Sine squared plus cosine squared is 1. And a matrix is orthogonal if and only if transpose times the original matrix gives you the identity matrix. And we just had that happen, so we have an orthogonal matrix. One of the things we can do with this idea of an orthogonal matrix is generalize the rotation matrix. One of the really nice properties about the rotation matrix is that every vector you give to it comes out as a vector with the same magnitude, just in a different direction. The rotation matrix restricts that by showing that every direction change happens in a very predictable way and in a consistent way. If we relax that a little bit, we can look for a matrix transformation that takes vectors and transforms them into a new vector in the same magnitude in a different direction, but doesn't have the nice rotational properties. There's a little bit more involved in what's happening there. We call that sort of a transformation, excuse me, we call that sort of a translation an isometric transformation or an isometry. Sometimes you'll see it as a length preserving transformation, but I use isometric. Isometric means that the size is going to stay the same, but we're not going to make a prediction about which direction it's going to end up in. Isometric transformations can take on any of several. And so we can codify that an isometric transformation, also known as an isometry or a length-preserving transformation, is any vector transformation T. Notice here I never said linear. Any vector transformation T such that the magnitude of T of V is equal to the magnitude of V for every vector V in the vector space. Let's let Q be any n by n matrix. The following claims are equivalent. First one, Q is an orthogonal matrix. The second one is kind of messy. For every vector x and y in Rn, the dot product of qx with qy is equal to x dot y. That's actually a surprisingly useful result on its own, but mostly it's in here as kind of a placeholder, because the last conclusion, not a surprise, I hope, based on the definition we just gave, Q is an isometric transformation. It turns out that orthogonal to isometric or isometric to orthogonal is very difficult to prove. And so our proof strategy is going to rely on two. We can show that orthogonal implies this weird thing about dot products, which implies isometric. And we can show that isometric implies this weird thing about dot products, which takes us back to orthogonal. Right? It's a lot more jumping around than we usually do to prove that things are equivalent. We have to do 4 steps instead of 3. But I want you to think of that as why that second claim is there. We're introducing it because it's a nice intermediate step going from here to there that we don't have to worry about writing out. We can give a nice name to. All right, so let's prove that statement 1 takes us to statement 2. Statement 1, remember, is that Q is orthogonal. So I want to assume that Q is orthogonal. I know that was still on the screen, but now it's not. Right. We've proven that since Q is orthogonal, that means that Q transpose times Q is I. The dot product. We don't do this very often, but when we started talking about matrices and the matrix transpose, one of the things we mentioned is if you treat X and Y as column vectors, you transpose X to turn it into a row vector, and then you take a row vector and multiply by a column vector, you get a singleton matrix whose result is whose single entry is the dot product. So we can say that X dot Y is the same thing as X transpose times Y. A singleton matrix and a real number are equivalent in every way that matters. Another blast from the past. If you want to take the transpose of the product of two matrices, you get the product of the transposes, but in the other order, B transpose, A transpose. Those two manipulations are the key to this proof. Because if I take QX dot with QY, well, that's the same thing as QX transpose times QY, and that's the same thing as X transpose times Q transpose times Q times Y. And if we group Q transpose times Q, that's the identity matrix. Multiply anything times the identity matrix, you get that thing. And then undoing what we did in the first place, X transpose times Y is the same thing as X dot Y. All right, that's just one part. That's not the entire proof. So a couple slashes to say we're done with the first part. All right, now let's go from 2 to 3. This time we want to assume what we just proved in the last one. Assume that QX dot with QY is equal to X dot Y for every vector X and Y. Now, let's take the norm of QX. Well, remember the definition of the norm? We talked about that fairly recently. The square root of the dot product of the vector with itself. So we're looking at QX dot with QX. And if we just assume that X and Y are the same thing here, then QX dot QX is just equal to X dot with X, and the square root of X dot with X is exactly the definition of the norm of X. And if the magnitude of qx is equal to the magnitude of x, that's what it takes to say that Q is an isometric transformation. All right, time to go the other way. Now let's look at going backwards from 3 to 2. Assume that Q is an isometry. Isometric transformation, I'm tired of writing all those words out. This is the ugliest technical part of the proof. I claim that for any vectors x and y, you can write x dot y as 1/4 of the norm of x plus y squared minus the norm of x minus y squared. You can prove this using properties of the dot product and properties of the norm and properties of vector addition. And I'm going to ask you to do that part, but this is something that we need to use as our basis to get the rest of this proof. So for now, we're just going to accept that as given, and we're going to build on it. I want to use the fact that Q is isometric to look at exactly this starting point. X dot y is equal to 1/4 of the norm of x plus y, the whole thing squared, minus the norm of x minus y, the whole thing squared. And then, since I have an isometric transformation, if I took the transformation Q on x plus y, it would not change the norm. And if I took the transformation Q on x minus y, it wouldn't change the norm there either. I can use the distributive property to write this separately as qx plus qy, and the second one separately as qx minus qy. But now what I have done is I've gotten it back into this form. I'm using qx where I used to use x, I'm using qy where I used to use y, but that's happening in the first one and in the second norm. So using that same claim that we had before, this must be the same as qx dot with qy. Right? I admit that's not a very satisfying proof because that is a really nasty looking claim, although in practice it's not that hard to prove, it's just cumbersome. But that takes us back from 3 to 2, and then all we have to do is finish up going from 2 to 1. Let's assume again that qx dot qy is equal to x dot y. Now let's name the columns of Q as little q1, little q2, down through to little qn. And remember, step one, or property one, was that Q is an orthogonal matrix. So what we're trying to show here is that Q1, Q2, down through to Qn forms an orthonormal set. And the way we're going to do that is a little bit interesting. I claim that for a standard basis vector, EI, if I take Q, matrix Q and dot with EI, I will get the vector QI. This is an idea that we have used previously, but I'm going to state it here as a claim. It's something that this is going to hinge on that we haven't really established. But building from that, if I take QI dot QJ, I can use this substitution and call it Q times EI dot with Q times EJ. And now I assumed that property of Q, Q dot X, Qx dot Qy is equal to X dot Y. In this case, I have the unit vectors holding that position. So QEI dot QEJ is EI dot EJ. And that has exactly the properties we want. EI dot EJ is equal to 1 if I is equal to J, and this is equal to 0 if I is not J. That's exactly the property we want in order to conclude that we have an orthonormal set. And if those column vectors form an orthonormal set, that means that Q itself is an orthogonal vector. And that was the last piece we needed. A couple of somewhat unsatisfying points in there, but sometimes that's the interest of these. What properties, and sometimes what weird esoteric properties, do our proofs hinge on in order to be able to complete them? I'm going to ask you to look at those properties a little bit more closely. But before I do that, I want to wrap up with one last theorem on properties of orthogonal matrices. For any orthogonal matrix Q, I claim that Q inverse is an orthogonal matrix. the determinant of Q is either 1 or -1, and if we have an eigenvalue of Q, that eigenvalue must be positive or -1. I also claim that if I have two orthogonal matrices, Q1 and Q2, let's let them both be orthogonal. Then their product, Q1, Q2, is also an orthogonal matrix. These properties are going to show up, probably not all of them, but several of them are going to show up in the problem set for this week, homework problems for you to work on proving on your own. They're not that bad. They're a little bit more involved than what I want to use for an end of problem video. So for the end of this video, I want to go back to those two claims that we made earlier. I want you to prove that for any vectors x and y, x dot y is equal to 1/4 of the magnitude x plus y squared minus the magnitude x minus y squared. And the tip I'm going to give you is that this is a much easier proof if you start with the right-hand side and make your way to the left-hand side. Starting with the left-hand side and trying to get to the right-hand side is going to make you want to tear your hair out. But going from right to left is actually not that bad. Just use properties of the dot product, properties of magnitude, and go from there. If you want to, I encourage you to also take a look at Q times EI is equal to QI. I'm not going to assign that one, but that was the other thing that showed up in the proof here that I said you had to take on faith. So if you want to play around with that, I encourage you to. I'll go through both of those in the follow-up video. But for now, that's all I have here. Thanks as always for joining me. I'll see you in the next video.